Nice to be here, everybody. So what I'd like to start with is, you know, a lot of us professors and teachers have given thousands and thousands and thousands of lectures, so to the point where it's really tough to give a lecture without finding new things in it. So I'm going to start with something a little bit new today. I want to say a short story that I think in general in life, my feeling is that you kind of need like a vision for your life. You know what I mean? Like, no matter who you are, and we can debate how long it is, but you know, I always say like you got to have a 5-year vision for yourself. I think it's kind of important. And the funny thing I'll say about this is, and I wasn't going to say names, I know Prasad's here, is a friend of Prasad of mine. One of the reasons I'm here is Bill Shanidis, who is a great researcher and friend of mine and collaborator at Georgia Tech. And one time I told him when I first became a professor, he's one of my mentors, and he said, "What are you doing?" And I said, "Well, I'm trying to formulate my 5-year plan, my vision." And he said, "Well, that's the craziest thing I ever heard, because if you get a vision, you're just going to change it anyway, so why have a vision?" And so I thought that, I think he wasn't totally serious, but he was kind of giving me a hard time. But with that said, I'm going to say my vision, what I think it is for the next 5 years. And multidisciplinary, multicultural is two of the important words in my vision. I think the environment, being involved in the environment and working with Jim, which I'm doing now, we have different expertise. I think really environmental health requires lots of different disciplines. Multicultural, I think it's really important for all of us to have multicultural experience, to understand other cultures, and for our students to have those same experiences. And I said researchers and students, multicultural, multidisciplinary, and collectively work together to make the air and water cleaner, and that's kind of my vision. I added water here because although most of my research has been done in the air, I'm becoming increasingly convinced that the combination of air and full water is a really important thing that comes together to exacerbate health effects worldwide. Okay, that's my vision. I might change it, like Bill said, in the next day or two, but that's my vision right now. So this is a paper that kind of describes some of my interests in general. I'm interested in really, really hazy areas, really polluted areas. I started working around 99, late 90s. I first got interested in China because it was so hazy there. This shows a rural region of China. You see that filter on the upper corner is when you suck the air into that filter. Visibility about 1 kilometer. Small little farming, agriculture, burning agricultural waste, plus small little cooperatives doing industrial activities. And this was what makes China still today a rather polluted place. So I first got my interest there. This is Hannah Cates, who is an undergraduate student at Georgia Tech, and took this picture, which I really like. This is Vietnam. This is brick kilns, where they make bricks, and a lot of countries are developing there. Also need a lot of infrastructure. They're making bricks like mad. They're burning all sorts of stuff to make those bricks. This is a filter that came right out of those brick kilns, right out of the stacks. But what I like about this picture is this is a really hazy area, but this picture was obviously taken probably really close to a rainfall that cleared out the air, and you see the white clouds in there, but it probably wasn't white for long, or blue skies for long, and probably very quickly became polluted there. I'm interested, there's a lot of pictures of this, I show this one sometimes. My interest is mostly is particulate matter, and this is 500 nanometers right there, so that's about a micrometer this wide. And there's all different shapes and sizes of these particulate matter, and they're made of all sorts of different things, so they're really complex mixtures. And so originally we thought that this would make for an extremely complicated story as far as how these things influence climate and health. And I think to some extent that's true, although we came a long way in understanding what the important properties of these are for health and the environment. And I'll talk a little bit about that. I've showed this picture like many people thousands of times, but so the two things I think about when I think about air quality is I think about the influences on climate and the influences on human health, and I guess you could kind of put agriculture in there, but mostly today I'm going to talk about climate, and I think you've seen this at the top, CO2. Let's see if I can get this right before CO2, this is a warming, it's an IPCC report, 2 watts per meter squared of energy absorption in the atmosphere. And then you come down here, this is the aerosol, the direct scattering by aerosols, and aerosols making clouds more reflective. If you kind of add this up, it's a negative effect of a couple watts per meter squared. So it looks on average like the aerosols have a global cooling effect that might kind of offset the global warming. So like at first cut, it looks like the aerosols might be important for climate. Okay, I want to talk, I'm just going to talk briefly at the beginning of my talk about climate, because I'm interested in climate and the effect of aerosols, and climate is a big part of global environmental health, and then I'm going to move on to more things related to human health. So this is kind of the way the aerosols can influence climate directly. This is by scattering and absorbing energy. And what happens is energy comes down through the Earth's atmosphere. Some of the energy is absorbed by these particles, some is scattered back to space. You have a reflective surface, some's reflected back up, and this whole thing happens again. And you put these particles in the atmosphere, and if you have a white surface like snow, you put white particles over that surface, it doesn't influence the top of the atmosphere energy balance much. You put black particles over, you get some absorption going, because you have absorption down, and then the snow surface scatters energy back up, you have absorption in the atmosphere. Also, over dark surfaces like land, these aerosols tend to be white, a white reflective effect. I'll talk a little bit about that. And this is kind of schematic. There's all these technical terms for those of us who are really involved in this that are the aerosol properties, which I won't talk too much about those aerosol properties in climate. I'll mention the bigger picture, important parts of it as I go. And what fascinated me, and I still don't understand why everybody isn't really interested in this, but what first fascinated me about 15 years ago is this is the visibility across the United States. And what you see is east of the Mississippi, the visibility is typically 30 to 50 kilometers. West of the Mississippi, the visibility is a couple hundred kilometers. And this visibility, the reason you can't see far is because there's a lot more particulate matter in the eastern part of the United States. Okay? And so I lived in Colorado, in this part of the country, and back in 1999 I moved from here where it was really clean. I moved to the southeastern United States because I was interested in studying particulate matter and climate effects, and I knew it was very hazy here. I knew that there was a real effect here, so we moved to the polluted part of the southeastern U.S., moved to Atlanta, Georgia, and so the first thing I did is I measured in the atmosphere what you have to measure to figure out how much energy is being scattered back to space by these particles over Atlanta, and this is a month-long period in Atlanta. This is the amount of energy scattered back to space on average. Each data point is point. Amount of energy scattered back to space on average by these aerosols over Atlanta. And it turns out it was on average, about minus 15 almost watts per meter squared. So 15 watts per meter squared is being scattered back to space by these whitish particles over Atlanta. And then we knew at that time that the CO2 forcing was a couple watts per meter squared. You know, I was like, wow, that's really amazing. That's a huge, huge amount of energy being taken out of the atmosphere above Atlanta. Of course, we're interested in health too, and then what's interesting, and then I saw this paper, and this has been revised. I should put a revision in it, but because there's new data on this, but it looks the same. This is a temperature trend over the United States for the last 100 years, and if you look, the western U.S., so the skin tones to blue are over the last 100 years. This is by the temperature record. You've had cooling, and the sort of hotter ones are warming. So it's warmed most throughout the West, but if you look over the southeastern United States, the southeastern United States is on average cooled by about a half to 1 degree. So the reason that I first got interested in this is because I moved to Atlanta, I was studying climate, and then I got invited by the local newspaper to go to, it was like a town hall meeting about climate change. And basically they had all these guys who didn't know much about climate, but all they said was, listen, I know the Earth is not warming because I know that it's cooling over Georgia, okay? And I was like, I just moved there. I didn't know what the heck anybody was talking about. You know, I was like, cooling. So I just kept my mouth shut, luckily. It's like, I better go check this out before I say anything. I said, well, I don't really know about that, but I know it's really hazy over Georgia. They're like, well, that's not what we're talking about. We're talking about cooling over Georgia. So sure enough, this goes right in line with what I'm saying. Probably this large cooling effect is a haze effect over the southeastern United States, and indeed, as power plants begin to emit less SO2, I'd be willing to bet that it's actually going to start warming up a lot more over the southeastern United States. That's kind of what I want to say about that. I'm still interested in that. We can talk more about it if anybody would like. And the other thing I would say is, if anybody wants to stop and ask me a question as I go, that would be okay too, because I'm going to talk about a few different things, and they're related in my mind, but it might be easier to do that, okay? Or you can wait till the end too, either way. The other thing that I've been interested in for a long time, because we're talking about global environmental health, is the Arctic. I'm interested in aerosols and how they affect the energy balance. I think all of us know this is a temperature trend in the Arctic. The Arctic has warmed much faster than everywhere else. And in fact, the Arctic is warmed by, it depends on how you want to dice and slice this, but 3 to 4 degrees the Arctic is warmed over, compared to the sort of 1 to 1.5 of the rest of the Earth. So I've always been really interested in the Arctic, and I grew up in Minnesota, and I really love snow. So, and I like mountains too. So this was what we knew. This is 2008. I can't quite see this very well in this picture, but that's not a big deal. This is Denali, right? Just got its name changed. That's a really interesting story, but it's called Denali now. It used to be called Mount McKinley. You see this haziness over here, and in the 70s and early 80s, everybody realized it was wickedly hazy in the springtime in the Arctic. So the Arctic, this pristine region, it turns out that this has a lot to do with from anthropogenic emissions. It's sort of the upper part, or the sort of in the northern hemisphere by sort of Europe, including Russia and the United States and some other countries. They emit stuff that gets up there and makes this haze. So we knew it was getting pretty hazy in the Arctic, and we knew it was from us. This was called Arctic haze. This was discovered before probably half of you in the room weren't alive yet, which is hard to believe. You can believe that, Prasad? You know, people here, we were studying Arctic haze when we were in graduate school, and some of you guys were not even alive. That shows how old we're getting. But so what's interesting, a couple of these manifestations, and I'm almost done with my climate part. I think you guys might have heard this, but it used to be that every year the sea ice would stay, the whole Arctic would stay packed in with sea ice. And every year it's receding a little bit more, and now there's less and less sea ice. And this is a manifestation of the fact that climate, the temperature has been warming in the Arctic, and one of the things we've been always talking about is why is that temperature warming? And the other part of it is as you get less sea ice, you get this positive feedback situation, you get more absorption because you have less ice, so it's this real positive feedback warming. One thing I've always been interested in, I should update this slide, I just realized I put in this one, but this is the Greenland ice sheet. I don't know if you guys know, the Greenland ice sheet at the very top is like 12,000, 11,000 feet. And in the summer, the warmest it gets, it never gets above freezing. But what happens every year, the top layer of the Greenland ice sheet melts a little bit. It turns, and this is 1996, 1998, 2007, 2012, the entire top of the Greenland ice sheet melted, just a little layer. And it turns the Greenland ice sheet from being white to almost being black. There's this huge energy effect, and there's been a lot of worry that this is going to accelerate the melting of the Greenland ice sheet, and there's some evidence that that's happening already. And again, this is from warming of the Arctic. And I've always wondered, why is the Arctic warming? We've thought CO2, we've thought the positive feedback, but I always thought that maybe these aerosols we're putting up there had something to do with it. This is the top of the Greenland ice sheet, so I've done a bunch of work up at the very top. It's 11,000 feet actually. And so you get there, this is, I don't want to talk too much, but we make all sorts of measurements in the air. These are measurements of aerosol loading and also measurements of how black the aerosol are, because when you do incomplete combustion, you get these black sooty particles, so it's kind of the sooty amount and the black amount, and sometimes the Greenland ice sheet sometimes is cloudy, but a lot of times it's really, really clear. So when it's clear, these aerosols are wafting over, sun's trying to come down, some's getting absorbed, some's getting scattered, it's affecting the energy balance of the atmosphere. And oh yeah, because I'm from Minnesota, I just want to say it real quick. Snow's really interesting. So if you look at the top of the Greenland ice sheet in snow, this is what the snow looks like sometimes. Sometimes it's like really fluffy, you know, like this. So sometimes it's super reflective, almost 100% the energy coming down gets reflected back. And then other times it's kind of cool, it's like these little teeny crystals. It's not quite as reflective, it's a little bit darker. And that lightness and darkness affects how much energy is being from the atmosphere a lot. Because like a photon might come down, if all the photons get scattered back up, the stuff in the atmosphere gets 2 chances at absorbing. But there's all sorts of geophysical explanations for this snow crystal stuff, which I think is really, really cool. And yeah, and I know my kids were asking me, you know, when it was snowing, did you guys see that? It wasn't really snow, it was like these little ice crystal chunk things, you know what I mean? So they were like, is this snow? And I'm like, well, I don't think it's really snow. I think it's called grapple or something, a technical name for it. And they're like, nah, it's snow. And I was like, no, it's not really snow, you guys. Anyway, so then like, well, what is snow? So anyway, we're having these discussions all weekend long. What is snow? My kids say it snowed, I say it didn't snow. I don't know what you guys think. I did see some snow in there, but I think that's not what it keeps it. So what we did is we went up there, I'll just say real short. This is a total amount of energy. Now over snow, you put the white stuff that goes in there, like, you know, stuff from power plants, sulfur dioxide makes sulfuric acid particles. It's mostly white, but you know that stuff, that black stuff you see from diesels and from burning, the black part of the particles, and that was on my filters, that stuff absorbs and can warm the atmosphere. It turns out these white surfaces that soot stuff absorbs. It's a net absorber, it does scatter, but mostly absorbs. And this is the absorption this is at the beginning of the day, at the end of the day for 2 different days. This is the amount of energy absorbed for 2 different days over the Greenland ice sheet. We measured it, all the parameters he had to measure, and we estimated it. It's really amazing. You get like 15 to 20 watts per meter squared. On average, over the summer, it's about 12 to 15 watts per meter squared of absorption. So remember that CO2 can absorb a couple watts per meter squared. So anyway, you have this huge absorbing nature of aerosols. It's not huge, but you have this huge absorption effect over these snow surfaces. A lot of people have worried about the stuff depositing in the snow making it darker or making it melt, but we've kind of been able to show that even in these pristine areas, this soot wafting from North America and Asia in Europe has a big effect on the energy balance. Now we're trying to figure out if it actually has enough to really enhance the temperature that we see, because going from energy to temperature is pretty complicated. Okay, all right. Oh yeah, and another thing, because I said this is an educational part, we also had a middle school teacher up there with us, and he was video linking back to his class, and we have can't see, we have a solar sensor measuring what's coming down, we have a solar sensor measuring what's coming up, and he was spraying black carbon all over the snow to see if actually we could see an effect, to show his class that this blackness, these particles that could deposit up there, were affecting the albedo. It's really not important up here in Greenland, this albedo effect, but it's something, it was an experiment that he did for his class, and that was really neat. Oh yeah, also, I should say, for those of you who are interested in Arctic research, or Antarctic research, I should say, this was actually observed a long time ago, this effect of the black carbon depositing the snow and melting the snow. So, second part of my talk, I know everybody's seen this a real lot, is I want to talk about health, and I think, I won't go on too long about this, but I think of the global burden of disease, everybody knows there's several factors there to do with air quality, and the one that we think a lot about, probably like, I don't know, I think the one that people like me and Jim think a lot about is this ambient particulate matter and its effect on human health. And what's really weird, and you guys probably know way more about this than me, but I'll just say this to be provocative, is like water doesn't even come in like the top 20. So like if you're a young person and you were going to study something that was important just based on this, you would not study water quality. Okay, and I think that this must, I think that these estimates must not have been correct. I think there must be something wrong with it, because I think, having been to a lot of developing countries, I think water is clearly, and seeing the water that people are being exposed to and drinking, I think water must be much higher up on the list than it shows here. And I bet in subsequent estimates it will be, okay? Right. Yeah, I have a few other things I want to say, but I'll say them in a second. So, and of course, I think a lot of people also, and I think a lot of you folks know here, a lot of that global burden of disease is driven by this cooking that takes place worldwide. These cook stoves where people burn indoors, they burn things to cook, they burn biomass, they burn dung, and they make huge amounts of smoke indoors, so especially women are exposed to these super high concentrations of particulate matter, okay? So this is this cook stove thing, I'll come back to that. I kind of became interested in this before I knew anything about, well, I knew about cook stoves, but this is the Himalayas. I did some work in the Himalayas where the air quality is super bad, and then we figured out the air quality was bad in the Himalayas is coming from India. And this is India, this is the Gangetic Plain, this is New Delhi, 1,000 micrograms per cubic meter. I'll mention this in a minute, but roughly 10 to 20 is considered healthy, so this is 2 orders of magnitude above the healthy limit, something we've heard a lot about. Photos in China, this is Harbin, China. I think that it used to be, I used to tell my air pollution class back 15 years ago that whenever I saw a story on air pollution, I would put that out and bring it to class, but over the last 5 years, I don't do it anymore because there's so many about China and India. We know the air is really bad there. Also, this picture was taken 10 years ago. This is Atlanta. This is visibility, like in that map, about 30-kilometer visibility. You can see this haziness looking towards down on Atlanta. Okay, so this is kind of what got me, some more pictures that got me interested. Okay, you guys might know, I usually keep my eye on this number here, annual average for, the EPA says annual average 12 micrograms per cubic meter. Even though there's a daily average, what I figured just to be safe for my kids is I don't really want to live anywhere where there's more than 12 micrograms per cubic meter, okay? That would be my, as a parent, and its advice to others. And one thing, so what's interesting about Atlanta, and I'll talk about the southeastern U.S., one of the most polluted cities in the southeastern U.S., is this is 24 hours, this is each hour what the particulate matter concentration looks like. This particulate mass less than 2.5 micrometers, and again, you tend to get a peak in the rush hour, then you get a trough in the afternoon, and then it kind of builds back up. And so this rush hour peak, it's typically over 30. And again, if I followed my rule, this is the most polluted month, by the way. But if I followed my rule, let's take the most polluted month, and we're down here at 12 would be safe. So, and this is one of the reasons, truth be told, that I don't live in Atlanta anymore, because my son has light asthma, and my wife has a little bit of asthma, and we're like, why are we studying air quality, and we're sitting in one of the most polluted cities in the United States, right? And so I always said, well, I go, this is where I am most of the time, you know what I mean? And I'm like, well, it doesn't seem like it's that high to me, But the truth of the matter is it was high, and my wife was like, you got to face the facts. We're exposing our children to unhealthy levels of air pollution. So I want to talk a little bit about the sources of air pollution in a lot of our cities and cities worldwide. I want to use Atlanta as a case study. I won't, I'm going to skip these. What we did in Atlanta is, and this is what a lot of the world looks like, and I'm going to tie this into the cook stove stuff, I hope in my final message. So this is Atlanta, this is during rush hour, so we had a study where we'd start at Emory University, we measured black carbon. So typically a couple % of the total particulate mass is what we call black carbon. It's that black stuff from incomplete combustion that looks black, little black particles. So this, we started Emory, and then we would make people go and hammer them into rush hour. They'd go in rush hour, and then they'd come back to Emory. And what you see is when you go into rush hour traffic, you go, this is we have 10 here, but it should be 12. When you go from rush hour traffic, you can actually get sometimes 40, 50 micrograms per cubic meter. That's just black carbon. So total aerosol mass has a couple hundred sometimes, not always. And these are what we call events when you're high, when they're very high. But in other words, in places like Atlanta, even though you have this background haziness, your exposure, if you're a commuter, which could be for an hour and a half a day on average, is huge in these cars, and you're being exposed to very specific. This is actually this peak right here, very specific sources. Yeah.
How much does it vary? Like, so if you're on the highway, it gets to be this high, but like if you're in the city and not like in by smaller streets, is there a lot of spatial variability?
That's a great question. So the question is you know, you're on the highways, but what does it look like on the side streets too? Right. So I can't. So that's a good question. The answer, I'll tell you. Let's see. I wish I could tell you exactly from this plot. At least one of these peaks is a side street. I can't remember which one. It turns out that the side streets sometimes have very high pollution because it's just like these. If you have a car here and there that's a super high emitter, then you get a really high waft in your car. So in other words, we used to do, when we first started doing this, we drove bikes all around Atlanta, and we were shocked at sometimes the really nice neighborhoods had very high concentrations. And I don't know if it's the delivery trucks in the neighborhoods or what. So although on average you're worse in this traffic, it can be high on the side streets as well. Okay, answer your question? Yeah. I mean, we talked all about this for a while. That was really interesting. And just to show you this plot, this is kind of the way it looks. This is a state-run monitoring site where the state monitors particulate matter, and this is when you're on the road. So what the EPA reports and what we tend to think about for health is these state-run monitors, but actually our exposure can be vastly more huge. Okay, so this is a big. So the real thing to try to figure out health is what the real link is between your own exposure and your health, not this background monitor that's just going up and down, you know, based on different factors in your true exposure. And I'll just say this, and so then some people say, you know, are there health effects? I'll just say I did a study with my collaborators at Emory, and they generated this plot. I did the measurements in the vehicles, and this is exhaled nitric oxide. This is it's a proxy for respiratory inflammation. Okay, so if you have respiratory inflammation, I won't talk too much about the specifics. You breathe out more NO. This is the change in NO from pre-commute, and then this is during the commute, and this is 3 hours post-commute. And what we saw, this is asthmatics, and this is non-asthmatics. And to make a long story short, we saw that on average, we had, I think, 150 people. On average, when people are in this traffic, that they see they're under respiratory inflammation. Okay, so people, so you know, even people like all of us, these are the normal people. When you're in your car, when you're exposed to these high concentrations, there's definitely some health effect. Okay, on average. And one thing I'll say, because this segs into something I think is really important, is we also looked in Atlanta, and there's another bigger picture pointing all this. This shows Atlanta. This is interesting, and this is over the last 10 years. And what you see is these are the state-run monitoring sites. And this is the old standard. This is the new standard of 12 micrograms per cubic meter. These are all the old ones. They're all going down, and most of them are below the standard. There's one station that breaks the standard in all of Georgia, and it's going to put Georgia out of attainment. And one thing, the good news is that in Atlanta and over the southeast in general, we see particulate matter pollution going down, right? A lot of that's from SO2 control, and at least in Atlanta, a lot of this is also due to the increased checking vehicles out. What is it? The annual vehicle testing. That's it, right? So it's had a pretty big influence. We know we've teased out what the relative proportions there, but this one is above it. This is the whole state's out of attainment. And what's really cool about this is we did this project, and I think, and then again, I'm going to seg this into something I think is more big picture and important, is what I didn't know is here's where Georgia Tech is, here's where I lived in Atlanta, and one of the largest rail stations or rail yards was in the southeastern US, and it was really close. I never knew that when I looked in Atlanta. And of course it makes sense because the original name of Atlanta was Terminus, right? It was the one of the main railways. It was the hub of the activity in the Civil War, so that makes sense. But it's huge, and somebody 20 years ago decided to locate this monitoring site right here next to the station, right? And that's before there was such thing as air pollution scientists or engineers, I would assume. And so this is the one station that's putting the whole state out of attainment. So we did a real simple project, and we took 2 sampling locations, and this is going to be the engineering part of my talk. And we figured we'll just watch when some days the wind's going to be blowing this way, and this will be upwind, and this will be downwind. Some days the wind's going to be blowing this way, and this will be upwind and downwind. We're just going to see what happens, you know. And I just remember, so we wanted to go in the rail yard and make these measurements. And this is CSX and Norfolk Southern. Those are 2 huge rail companies, and they said no, you can't go in there. So we sent them our sample plan. We sent them our proposal that was funded from the Georgia Environmental Protection Division. And they said that it's not going to work, what you're trying to do. And then we said, well, how about we come and talk to you? And they said, no, we know it's not going to work. And I said, well, how do we know it's not going to work? And they said, because our experts say it's not going to work. And I said, well, can we talk to your experts? And they said, no. so we didn't get in there. And I said, I just want to let you guys know that, because I think we all have to work together. I said, I know it's going to work, and we're going to come up with some results, and we'd like to work with you to show you the results. We can work the whole process with you, and if you think something's wrong, let's really talk about it scientifically. And they said, nope. And I said, well, okay, but you know, that's the way things went. And so it was easy enough. So we had stations upwind and downwind of this rail yard. You can see we measured the black carbon, those particles, because the diesel trains them in. We measure carbon dioxide because that goes up because you're burning fuel, you make more carbon dioxide. And this is so this is the upwind site. Hang on. The 2 dashed lines is the upwind site for black carbon and CO2, and these are the downwind site for black carbon and CO2. It's pretty easy. And whenever the wind would blow from the directly at us, we had upwind, downwind. We go make sure trains were coming. We see it time after time. And then what you can do, what's really interesting, is you can take the CO2 concentration and black carbon concentration. I'll come back to this, and you get something called the emissions factor. That's the amount of carbon emitted, or amount of black carbon emitted per amount of carbon consumed. And then if you know something about like the fuel use in your source, could be the roads, could be the rail yard, you can use a simple dispersion model to put in that fuel use, put in the emissions factor, and estimate the spatial field of the pollutant of interest, in this case black carbon. It's very simple. It's really engineering in the grand scheme of things. And so we did that. What's really interesting, let's see, so we ran a model called AERMOD. It's a very simple Gaussian plume model, and it's not very complicated. We ran it over a year with the meteorology of the city. We put our emissions factors here. We did know they do have to report to the state the fuel use, so we knew that. And what you see is these are like isoplecif concentration. If you go to Fire Station 8 where this is, it shows that this is, so here in this little thing, the rail yard adds 2 micrograms per cubic meter to the surroundings, and here it adds 1. In the grand scheme, that's not a lot. But it turns out that, interestingly enough, that's almost exactly how much is over the standard, right? So our very simple approach with measurements and modeling combined helps solve a really interesting problem of how a source contributes to the concentration field around it. Okay, I'll come back to this, right? So that wasn't very complicated. So we wrote a paper on it, and a couple papers on it, and I don't know, we never had any contact with the rail yards about this, but I hope they saw it. The state did see it. The state's trying to figure out how to either make that station not be a monitoring site anymore, or make the rail yard emit less. Oh, in fact, I forgot. So the state got $38 million because they're going to try to put the new generation of I forget, they're called switchers. They're the things the Thomas the Tank Engine things that go around connecting all the trains, and they're going to get all new ones in that yard. That's what they thought was creating the pollution. The state got $38 million from the federal government to do that. So hopefully we're going to go back and see if it really worked. So we're thinking here, one thing I didn't tell you about these measurements is these upwind and downwind sites cost about $150,000 each. The equipment was pretty complicated, not so complicated, but it also required a lot of oversight. So it required really skilled technicians and graduate students to keep running. So we're like, well, that's all great, but we want to be able to do this in a lot of different places. We want to be able to blanket these around sources and around places where people are worried about the air quality, so we can figure out what sources are contributing to the air quality and give people information. And for many, many years, because I'm a measurement person, people have written me and said, could you please come make measurements on, I don't know, Cote d'Ivoire, Kathmandu, Lapaz, Bolivia. It goes on and on and on. I always had to say, listen, we don't really have cheap instruments, and so maybe we could try to get money to get a project, but if we could do it cheap, we always thought, well, just send things to these people. Send a little box to these people, tell them how to put it up, and then they'll go online and we can look at the data. So that's what we're trying to move towards. And so Caroline Johnson's here. Caroline, this is some of her pictures, and she's working on this. We're trying to figure out how to use really low-cost sensors to get concentrations of important pollutants. In this case, this thing here is 5K. That's a black carbon instrument, so that we don't count that. But we have carbon dioxide, particulate matter. That was what we had before, more or less. Particulate matter, black carbon, CO2. And then we have, and then we can measure wind speed, wind direction, and things like that. And we can actually have a lot more sensors that measure a lot more things now. And then this right here is an Arduino computer. And does anybody know what these are? Does anybody know what these Arduinos are? Right, I know some of you guys do. I mean, it doesn't seem like a lot, but it was 10 years ago. If we wanted to make measurements with something, we'd have to probably try to use a computer interface. So you'd have to have a computer sucking the data from this thing. Not exactly, but that's one way. Or we'd use very expensive data loggers. And what's happened now is it's $30, $40 computers now that have lots of inputs and outputs. And these things, you can communicate with them, write programs, and these things have really revolutionized the ability now to integrate sensors into environmental applications. So this computer with some new low-cost sensors that we've characterized a bunch. Most don't work, some do, some we modify. We're trying to make some in our own lab. I think it's going to make a huge difference in the next 5 years. I think we're going to make measurements all around the world, not just us, but everybody. We're going to really start to understand the environment. And I think that's where the environment's going to get clean. Okay, I don't want to talk about it. So I'll just say this. So for example, we've tested some of these low-cost sensors. This light color is the standard reference sensor, and this blue line is these low-cost sensors. And they actually line up pretty good with these sort of measurements we trust. So this is maybe some of the sensors now are tens of dollars compared to tens of thousands of dollars. That's kind of what we're talking here, tens of dollars versus tens of thousands of dollars. And so it looks pretty good to measure particulate matter. We're well beyond this now and have a lot better sensors even than we did here. But what's interesting is you can go into traffic in Atlanta. This is CO2 particulate matter. This is traffic in Atlanta. This is rush hour. And you can use, think about the sensors, if you're clever, you can use a couple different measurements. You can combine them, in this case, particulate matter and CO2, and you get these emissions factors. So like if you think about like cook stoves, for example, if you go and measure cook stoves all over the place, say in a bunch of different communities in India, I think what you're going to find is the emissions factors vary greatly as a function of the cook stove, what they're using, and lots of other things. So what you could do with this is you could go measure PM and CO2 at the same time. You could get a probability density function of the emissions factors, and then when you go to try to figure out the modeling of health exposure, you have this PDF of possible outcomes. And then also you have that data that can go into models that would help you estimate things like, like I know Jim and I were just in China, and people are saying, the global burden of black carbon is dominated by people cooking in rural villages. And to what I say, like, I can't believe that. That seems preposterous to me. I know you guys can sit in your labs and make those back-of-the-envelope calculations, but I've been in enough big cities where I see these huge sources of black carbon in diesel, and so maybe you're right, but I think what we really need is we need better measurements so we can quantify this. Okay? And there are papers out there that says that big cook stoves have huge fractions of black carbon. Say huge, I can't remember, maybe 50% or something. I can't remember. It's big off the top of my head. Okay? I think we're going to understand that problem. We have to make more measurements. There's no doubt. Okay, so I'm hoping I can only go 10 more minutes. I'd like to go. Okay. One thing I want to say, this is the education part. What I think is really important, I think more experiential learning for undergrads to inject that into undergraduate education would be great. And so one idea that we have is that you try to take freshmen and sophomore who are interested in the environment and health, in this case engineering, and you try to have an international experience where they go somewhere, they plan a field project, and they do something over spring break that's really important research-wise, and have team building, and then maybe learn something about the environment and health. Okay? So this is a class that I'm teaching this semester. Heidi Raylan is here. She's a teaching assistant who's taught this before. We did do part of this class last year when I was at Georgia Tech. I was part of it, so is Heidi. And we went to Lapaz, Bolivia, and I'll just say a couple things. This is what Lapaz, Bolivia looks like. This is getting back to the cook stoves as black carbon and what affects health. And also another thing I should add that is real interesting to me is I think the influences on health, although these cook stove estimates have dominated the global burden of disease, I think if you go into very highly populated areas and you factor in exposure, not just background concentration, true exposures, especially in places where you have a high diesel source, and if you factor in relative toxicity of the health impacts, I think what we're going to be finding soon is these mobile sources in a lot of cities have a huge dominant effect on global health as well. Right now, they're very low estimates. So anyway, you can see that's, I can't remember how, it's probably like 300 micrograms per cubic meter of black carbon, something like that, right? That's right on the side of the road in Lapaz, Bolivia. And then in Lapaz, just as a point of something I would never have known about, Lapaz has this thing called the teleferico that goes all around town, and it because they have, there's a lot of vertical stratigraphy, so getting from the valley up top can take a couple hours during rush hour. So they have all these telefericos, they call them, they're gondolas that bring people all around. I can't remember, it was like 40,000, 50,000 people a day are moved in these things. Do you remember what they said? Right? I can't remember. I wonder, I should know this because I'm a civil engineer, but like, I wonder why we don't have these things. Why can't we have these? And why can't we go from like the RTP gondola, like it goes from Raleigh to Durham to Chapel Hill. And you don't got to dig up, you don't have to dig up a whole bunch of stuff, put a tube in the ground. Why is that? I don't know. Anyway, it might be more expensive than I thought. But they set a tab on this. I think they said the tab was in the billions, like a few billions of dollars. I think we should have these things. But anyway, so we went there, and what we were interested in, one of the projects that we worked on with the undergraduate students, and this is all driven by undergraduate students, is what is your exposure in this compared to going, when you go down in the valley to work during the day and come back up, as compared to being in a taxi or something like that, or public transportation. And I'll show you, this is that black carbon particulate matter again. Here's the teleferico average concentration, and here's kind of the cars and buses that you would take. So the other thing is these things have just these huge, huge outliers, although on average, you're a factor of 10 to almost a factor of 100 less when you're in that teleferico. Walking, of course, is less too, but when you take the typical modes of transportation, the exposure is way higher. So in other words, if you're worried about these people's health, you have to be taken into consideration the exposure near the roads, okay? This is all done by undergrads, and they design all this as well. And okay, lastly, okay, I talk about the Taj Mahal. I know some people have heard too much about that. I've been talking a lot about this last year. This just stuff that happened to us. A paper that just came out. So the Taj Mahal, it turns out, I went to the Taj Mahal, and what I noticed, this is maybe 10 years ago. I noticed that this is what I took a picture of at that time, and asked them what was going on, and they said, well, the Taj Mahal gets brown, and every 5 to 10 years we have to clean it. I won't talk. You can't just power wash it. You can't wipe it off. There's a real special cleaning technique. They put a pack of mud on there, and then they let it sit for days, and then they take it off and do it a couple times sometimes. Very painstaking. And so right away I saw this, and I was like, well, it doesn't wash off, so they're particles almost for sure. They're not soluble in water, and they have a brown tinge, which I know dust and organic carbon from burning the black carbon has. So right away I was like, I know exactly what this is. This is insoluble particles that are depositing at the surface, and that's what's going on. But then, like always, it takes about often a short time to figure something out, but a really, really long time to prove it, right? So we did a study there, and we went, and took a couple of years. We went for a couple of years, and we measured the total suspended particulate matter and the fine particulate matter. We measured right there at the Taj Mahal. And basically what we saw, this is carbon. This is carbon right here. This is dust, and this is ions, things like sulfur and nitrogen from burning stuff. And this is the black part right down here. So that was no surprise. Very high concentrations, okay? And then we put these little targets up at the Taj Mahal. We put clean marble targets. They let us stick them on areas around the Taj Mahal. And then we let them sit there for 6 months and came back and looked at them. So we started with these clean marble targets, just like the Taj Mahal. And then afterwards, we got them. This is a picture. No, this is not a picture of one. This is a made-up image. Then this is kind of what they would look like. They would look kind of brownish. And then we zoomed in and looked at what was on there. We saw a whole bunch of particles, and then we looked at the particle size and composition. Okay. And I won't go. So this is an actual marble surface. The color was a little bit off-white, just about this white. After about 6 months, that's what this is a true picture of the marble surface. Then we zoomed in and we saw these particles on there. They were clean at first, and then we did the chemistry and size on them. And okay, I don't want to. So basically, I'll just mention real quick. Then what we want to do is we want to see what color the human eye would think that those. So if we took it all aside and I gave you and I said, here's the chemistry and the particle size on this white surface. Tell me what the color should be. That's what we did next. We came up with a real simple model to estimate color. It actually wasn't so simple, but a model to estimate what the color your eye would perceive a surface as if you put particles on there. That's kind of this whole process. We'll talk about that. Then what's kind of cool though is basically what would get popped out as a number from our model. And then the number is this thing called the Munsell color system. It's like color chips, when you go to have your house painted. They give you this book of colors, and basically we had to look up the book. This is all really, really super cool, and we could talk more about it, but how your eye perceives color and how these particles scatter and absorb energy and make color over a given surface is really interesting. Anyway, so at the end of the day, we had three components. Dust. So dust would go from white to this color if we just took the dust we saw. If we just took the organic compounds from burning stuff, you burn things that are organic, they make organic compounds. This is what the color would look like. If we just take the black carbon that we saw, this is how it would change the color. If we add these all together, this is how it would change the color, basically this brownish color. And it qualitatively estimates what we saw. Okay? So that was pretty interesting. And so this was in, I just photocopied it. We got tons of press on this. It was in January. It was on the cover of Environmental Science and Technology magazine. It was in, this is the article that appeared in the National Geographic. And when I was photocopying this today, I've seen this article a few times. But I noticed that here's what's on one page, and this is what's on the next page. So like when you open it, it looks like that. And I was thinking about this. This is really weird. I don't want to talk too much about it, but it's on my mind because I just saw it for the first time, even though I've seen this article. First of all, this is a Google advertisement, right? Second of all, they wasted all this white space, right? Third of all, it's about my article. So I think that Google owes me money. But But isn't that weird? I mean, why would they do that? Isn't that bizarre? A whole page article in National Geographic, whole page advertisement based on one of their, anyway, there must be, I don't know, what do you think about this? Does that seem like a good way to, like, you know, get PR for an advertisement to have a big, huge white space? Anyway, so I just noticed it. So the other thing I'd say is it got a lot of press. One thing that's interesting is I would say about this is, so about 2 weeks after our article, they banned dung burning and diesel vehicles supposedly in the city of Agra. And so within 2 weeks of our article coming out, somehow the Indian parliament had a discussion on this article, and then they banned, dung cakes has nothing to do, unfortunately, with the Taj Mahal's problem. I wish they would have talked to us, but, and also, so I thought about this, and they banned diesel vehicles and burning of any kind, they said. But what kind of got me worried is that the poor people in India, and almost everybody's poor in India on average, they burn dung for cooking. So it got me kind of, I was like, well, I don't know if that's a right solution. And then I knew from the back of the envelope calculation that the dung was not contributing majorly to the deposition. And then they said that they were going to give natural gas to everybody for cooking and new stoves, which I find hard to believe. We're still, we can't figure out what's going on here. I don't know what's up with it yet, but we're trying to look into it. And lastly, this just came out, when was this? I mean, Taj Mahal not turning yellow, government assures Parliament. I mean, which is totally not true. So, so that was it. It's been going on and on. What I want to say, and I think I'm almost done, is I have a few other slides. So what's interesting is this Taj Mahal effect of particles depositing, discoloring the environment. It's when I started to look at it, all of a sudden it became incredibly ubiquitous to me. This is in Beijing. This is a combination. This is mostly dust, but there's also this carbon from burning and emissions from coal burning, emissions from vehicles. And so you see it right here, you know. And this is, I don't know if you can see this. Me and Jim were there together. This is Tsinghua University. So this is the sign that says Tsinghua. It's a glass door, and I just took like a piece of tissue and I just rubbed it against the glass door again. This is, if you look close, you can't see it as well as I could, but this is not as much dust as it is soot and black carbon. Okay. And then I was in Iran, and I was in Isfahan, this is like this awesome mosque in Isfahan, super famous place. And so I can't help it because I'm always thinking about this, and it's really polluted there. So I was walking into the mosque in Isfahan. There's inside, I'm looking at it, I'm like, man, something's wrong with this. This looks pretty discolored to me. So again, I had a little piece of tissue. I rubbed the wall in the mosque in Isfahan, and I rubbed it a couple times. Sure enough, super dark. If you look really close, again, it's dust, and there's blackness and brownness to it that is not just dust. So this seems like a ubiquitous thing to me that this is going on. I think the natural cover of the environment is getting changed a lot in these countries with high pollution concentrations. Okay. And this is in Tehran. This is an arch in Tehran again. I was looking at this. I couldn't help it. It looked like there's a lot going on there, but it certainly looked like particulate deposition and maybe some other chemistry going on to me. Last thing. So I'm almost done. I want to talk. This is a project Heidi's working on. In India, it turns out one thing that is contributing a lot to pollution, I believe, and you know, we talk about these cook stoves driving human exposure and toxicity effects, which I think there's no doubt that breathing in those high concentrations of the cook stoves is dangerous, and there's no doubt it's affecting people's health. But then you have a place like India, these urban and suburban environments where everything gets burned. You can do a back-of-the-envelope calculation for all the trash being generated in India and try to figure out how much of that's being burned. It's probably something like 70 to 90% of the trash is being burned. And then try to put a few percent of that up into the air. It's a huge number. So I think you look, these are all different, you guys can't see them too well, but all sorts of different trashes burning along the side of the street. Anybody's been to India has seen this. These were where we sampled all around there. And these are what the filters look like. I don't know if you guys can see this good enough either, but they're, oh wow, look at, you can see that right there. See, you can see the colors of all the different ones. I don't realize I'm trying to back me exactly. But I just, my sneaking suspicion is that if you breathe in the different colors, that it's got to have some different toxicity, right? It's got to, I can't imagine. I mean, I don't know anything about medicine or physiology, or really the lungs for that matter, but I can't imagine that these things don't have different responses in the human lungs, because those things really go along with different burning conditions and vastly different things than what's being burned. Okay. We're thinking about that. Do I want to say anything about this? Let me skip this because it takes too long. This is the toxicity. We are trying to figure out how relatively toxic these things are by using different assays, and that's going to be a big part of our research for the next 5 years, I think. Okay, so I'm done, but I just want to say I think the next phase is trying to apportion sources to health effects. What does that mean? Well, that is like, so how much does diesel, gasoline vehicles, biomass burning, say in an urban area, how much do those things actually affect health? So look at the sources and their health effects. I think another big part, and this is something Jim and I are working on in China, is how indoor and outdoor pollutants come together to potentially exacerbate health effects. Indoor pollutants are a lot different. You can have emissions like gas-based emissions from surfaces, and also cooking, obviously, from biomass burning, and then you have the outdoor emissions, and then you can potentially have some different chemistry going on indoors. I think, I didn't mention this, I think that this haziness is screwing up people's mental health. I think that in China and India, when you wake up every day and you walk outside and it looks white and super hazy, I think that has psychological effects. I got zero proof of that, but that's my hypothesis. I think that developing these low-cost sensors is going to help us better understand air quality everywhere. And I think lastly, this is a social sciences issue. I think we have to figure out ways to get people interested to make the air better. The only reason I became interested in this is I saw what happened when people got worried about the Taj Mahal turning brown, and then so quickly the government moved. Okay, so the question: so are there other ways that we haven't thought of to make people get interested in air pollution? This is one. Like, I know I told this to Jim, and we could convince people in these really hazy parts of the world that their child's mental health was dependent on air quality in any way. They would have a heart attack. Well, they wouldn't have a heart attack. They would do whatever they could do to probably make that stop. I guess. Yeah. Okay. So that's it. I think I have a list of my a bunch of my collaborators. I don't know if I have them all in here, but I'm trying to think. I have a bunch at Duke too now, which I should list, and I know Jim should be on here as well, and all my students. I don't know if you're on here or not. But that's it, and we can take some questions.
Thank you very much for that very enlightening, since you actually have a 5-year vision. I don't have.
I want to see everybody's talking vision.
Anyway, questions? That's very impressive.
Yep.
So as bad air quality becomes just a normal way of life for the young people there, how do you think that will affect the motivation to actually make their cleaner? Because we remember, well, we're in a cleaner place generally, but if they don't remember the day that they could see the sky was blue, like maybe they just think that's the sky color.
Well, so there's this notion that there's sort of this gross domestic product per capita crossover, where when people are affluent enough, they actually start to worry about the air. Okay. So it's kind of the opposite of what you think. So I remember when I used to go to China in the late 90s, I'd say, oh my God, it's so polluted here. Doesn't this worry you guys? And they would say, well, you know something? The conditions in China were so much worse for living standards in the 80s. And then went through the 90s, it was pretty polluted. Now it's polluted now, but our living standards getting much better. We're all trying to make jobs. We're trying to, make better lives for our children. And then I'm not making this up. And then they said, but when all this happens, I guarantee you that people in China will start to make the air better. And that's kind of exactly what's happening now, right? So the question is, do we want to sit around and wait for that gross domestic product per capita cut point and just let everything take care of itself? The cook stoves has said the same thing. You can go try to make people use different cook stoves till you're blue in the face, but what's going to happen is eventually when they get affluent enough, they won't use them anymore and move into the city. So the question, I think we're trying to push back the time period that it's going to take for those people. Yeah.
Well, thanks for your presentation, Mike. I was interested in the last slide about, future work. You mentioned a couple of things related to health impacts, and I'm curious what your plans are for bringing in more health components into this work.
Yeah, well, I'd say, so I think now that people like me who study air quality, I think we have to have the health component in everything we do if possible. And so I think, so I'm working with Jim, and we're doing exposure and some health outcomes, but I think at the same time, we need to get more ingrained with the true medical people who know health outcomes. The other thing that I think is we've got to figure out toxicity assays for both acute and chronic health that are actually true representations of what happens to humans, right? So I think at the same time, we have to keep trying to pioneer which assays are important and relevant. Does that make sense? Right?
Yeah. Right, Prasad?
So Mike, the GBD analysis that you showed was based on a kind of analysis of, was it epidemiological analysis of health outcomes versus exposure based on monitors. It was epidemiological analysis.
What analysis, which one are you talking about?
This is the GBD and the global burden of disease.
Oh yeah, okay, right, oh yeah.
So they looked at kind of at regional levels, how many people were dying or whatever, versus what the ambient monitors showed. Now you're showing that the ambient monitors are not capturing true exposure.
Right.
So that would indicate that the toxicity is actually less than what GBD assumed, because they actually looked at people who were sick and dying and stuff. I mean, it's the same people who were still sick and dying. So how do you close this loop between, do you have to do a whole new analysis of this, or?
So I can't, if I told you that I understood exactly how they did their analyses, I would be lying. I know that the way they did their analyses with most particulate monitors doesn't seem very representative of true exposure. I also see that with, they assume some composition, some health outcomes. So, so your point is you have this dose response function that they used for some, other locations as a function of particulate matter, and then they apply those. And so I guess my question is this: do they really have the representative dose response functions? That's one, right? And I would say the answer to that is going to be no. And are the numbers going to go up? See, I don't know. If I had to make my guess, again, I would guess that there's been an overestimation of the cook stove effect, underestimation of the urban exposure. And the urban particulate matter per unit mass, I feel like I would have to guess is more toxic in general. That's just what I would guess. So where the estimates are going to go, I don't know. I mean, I'm not saying, I don't know how to close this. So I don't think
I guess the other,
If I can add, I think,
Yeah.
I think actually I disagree with you, Mike. I think
Okay.
the ambient estimate is much more accurate than that cook stove, because the available epidemiological literature is largely based on the ambient concentration. Prasad, this has nothing to do, they did not take into account of any differential effects of different particles or different things. It's basically, the poll, there's hundreds or studies around the world that you just defined a relationship about 10 microgram per cubic meter increase in PM 10 or PM 2.5 with a 2% increase in mortality, and then they go there, you find a population, and then just apply that simple math. Just this is a population times this dose response. That's the number of people we estimate they're going to be dying. People always ask me this question: say, how can you think this PM 2.5 actually going to cause people to to die? I said, no, it's not counting this one and then says this is that. It's based on, yes, counting the body, and then you have this continuous measurement PM, and then you do a statistical modeling.
Yeah, but I also,
I guess the real question, then the other way to ask the question is the variation of exposure that is represented by the PM monitors capturing the true variation of exposure of populations?
I don't think so. That's why you need a probably better kind of.
Wasn't the argument that somehow just with some low R squared value the ambient measurements, you know, sort of agree with exposure. Because I think also, and we were talking,
Because all the FP shows is you have the central monitor measured PM concentration, a population for the city, and you have that, you know, it shows significant association. That's all. You know, if you do a personalized thing, they cannot do it. You need the entire city population to do that. It's not individual level exposure data, individual level measurements. But cook stove, for example, there's very few studies to capture that kind of those responses. So they actually use the ambient-driven ones. So
yep, yeah, right. That's a good point.
anyway, so
I mean, I know what you mean, because I don't know, closing the gap, I don't know how we're ever gonna do that. I think we all agree air pollution's bad, let's just make the air pollution better, that's what I continue thinking.
I have a question.
Yeah.
You showed all those things. Now I thought I would believe there are places, so-called background areas, where you can actually find some sort of pristine air, whatever background study. Now when you showed that was the architect.
Yeah.
I don't know where we're gonna find it.
Yeah.
A background, true background.
The
Do you have any comment?
South Pole is one of the few places that seems to be the lowest concentration on Earth, but there's not there's too much because it's the southern hemisphere. Besides that, I haven't seen too many places that don't have some impact.
Because Himalaya, you see what you showed.
Highly impacted. Yeah.
Any other questions? All right, if no more, thank you again.
Thanks, everybody.